Okay, so this will be the second lecture in chapter 7. So in this lecture we dive into a little bit more of what the actual structure of an atom looks like. Okay, so from chapter 2 we have a current model of what the atom looks like, right? A very simple model where we have a nucleus and then we have an electron cloud. Right, so that's our very simple chapter 2 model. But it turns out that it's not quite this simple. The structure of an atom is actually much more complex than this. And so we're going to go through what's known as the Bohr model of the atom, which from a 1913 physicist. So in 1913, a physicist named Niels Bohr basically proposed a new model of the atom. So that's 1913, that's not a long time ago, right? So that's just over 100 years ago. So in about 100 years' time, we've gone from knowing very little about the structure of an atom to knowing an extreme amount of detail about the structure of an atom. Okay, so basically the Bohr model of the atom, so the nucleus, nothing changes about the nucleus, but it's just the Bohr model has electrons existing in shells about the nucleus, not just one big smear of electron density, but instead shells. So we'll go through the basically 4 different principles from this model to try to explain this in more detail. So first one, so electrons exist in shells, or sometimes called orbits or orbitals about the nucleus. And so the shells are symbolized by n, which can have values of n can equal 1, 2, 3, 4 on to infinity. And so, as n gets bigger, the size of the shell gets bigger. Okay, so these are the different shells. So this would be n equals 1, for example. This would be n equals 2. This would be n equals 3. This would be n equals 4. So as n gets bigger, the size of the orbital or the shell gets bigger. So where does the electron going to be most stable at, and which shell? Where it's going to be the most stable in the first shell, in n equals 1 shell. Okay, so why would the electron be most stable in the n equals 1 shell? So if the electron was here, why would it be most stable there? Well, electrons are negatively charged, and where are your positive charges at? Your positive charges are in the nucleus, right? So if they're in the first shell, then they're closest to, so there's an electrostatic attraction then between the positive and the negative, which is stabilizing. So being as close to the nucleus as possible is the most stable place for the electron. Okay, so each shell can only have a certain number of electrons, a maximum number of electrons given by this formula 2n squared, where n is the shell. So if you're at the first shell, for example, so if n is equal to 1, so 2 times 1 squared would be 2. So the first shell can only have 2 electrons. If you're at the second shell, so 2 squared, so n squared. 2 squared is 4, times 2 would be 8. Second shell can only have 8 electrons. Third shell, so 3 squared would be 9, times 2 would be 18. So third shell can have 18 electrons maximum. It's okay to have less, but it's not okay to have more. Fourth shell, so 4 squared is 16. 16 times 2 is 32. So the fourth shell can have a maximum of 32 electrons in it. And we could go on, right? Fifth shell, 5 squared is 25, times 2 would be 50 electrons. So why is it that you can put more electrons in, as n goes up, why is it that you can put more electrons in there? So intuitively, it seems to make logical sense, right? So again, so with the Bohr models, we have the nucleus, and then we have shells. So you can have an infinite number of shells. So this would be the nucleus. So this would be n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. So why is it intuitively, it makes sense that the fifth shell could have more electrons in it than the first shell. Well, One reason it's bigger, right? So if it's bigger, it can accommodate more electrons. Okay, so and then another main principle from the Bohr model, so you can move electrons between shells, but only if it absorbs or emits energy of a specific wavelength or a specific frequency. And so that's this concept that energy is quantized, and we'll talk more about that at the end of the lecture. So transitions between shells can only happen if the energy absorbed or emitted by an electron matches the energy difference between the shells. Okay, so why is an electron most stable in the n=1 shell? We answered that because it's closest to the nucleus, which is where the protons are at. So there are an infinite number of shells. So what does it mean if the electron is in the n=infinity shell? So if you had an electron in the first shell and then you moved it to the n=infinity shell, what does that basically mean? It basically means the atom does not have that electron anymore, right? It means the atom has been ionized. Right, it's now a cation. If it loses one electron, then it's +1 charge. If it loses 2 electrons, then it's +2 charged, and so forth. Okay, so let's practice the Bohr model. So let's sketch these atoms. So the sodium-23, bromine-79. So using our simple model, this would simply have 11 protons, right? And then if we subtract the 2, 12 neutrons, and since it's neutral, it would have 11 electrons, right? But if we use the Bohr model instead, where electrons exist in shells, then the nucleus is still the same, 11 protons, 12 neutrons. So n=1, n=2, n=3. So the first shell can only have 2 electrons in it. The second shell can have 80 electrons maximum in it. So that gives you 10 electrons. You need 11, so there's only 1 to go. So the third shell would have 1 electron in it, right? And if we did this for bromine-79, so again, just using our simple model or the Bohr model, this is a lot of electrons, so I'll just draw my shells like this. So we have 35 protons. If we subtract this, 44 neutrons. So it's going to be the same in both models, the nucleus. So now 35, so then you would have 35 electrons if we're using the simple chapter 2 model, but if we're using the more complex Bohr model, so this is n=1 shell, 2, 3, 4. So then we would say there's 2 electrons here, 80 electrons here. The third shell we said can have 18 electrons, so that's 28 so far, and we need to get to 35. So we have 7 more to go, so 7 electrons there, right, in the fourth shell. I think that totals right. 10, 28, 35. That would be 35 electrons, right? Okay, so let's take a couple more examples. So just using the Bohr model. So potassium 40 with a +1 charged. So we'd have 19 protons. So we got 19 protons, right? And if we subtract those 2, 1, 3, so 21 neutrons. And for chlorine 35, so 8, so 17 protons, 18 neutrons. And then, so potassium +1 would have 18 electrons, right? So then it's going to have 2 electrons here, 8 electrons here. That's 10, and we only need to get to 18. So then it's going to have 80 electrons in the third shell, right? And that would be 18 electrons. So Cl- -1, how many electrons is it going to have? So since it's negative, it's going to have one more electron than proton. So it's going to have 18 electrons also. So it's going to have 2 electrons here, 8 electrons here, and 8 electrons in the third shell as well. So these two ions have the same electron shells, same number of electrons in each shell, same number of electrons, so they're isoelectronic, right? Okay, so hopefully that makes sense. Hopefully the Bohr model makes sense. You just need to keep this in mind, how many electrons each shell can hold, and figure out how many electrons the atom or ion has, and then start populating the electrons from the inner shell to the outer shell until you get to the right number of electrons without violating the maximum number of electrons in each shell. But you have to fill it up before you can move to the next shell. So you have to put 2 in the first shell before you can move to the second shell. You have to put 8 in the second shell before you can move to the third shell, and so forth. Okay, so let's consider 5 hydrogen 1 atoms. So 1 proton, 1 electron, right? And that electron, where would that electron want to be at? It would want to be in the first shell because that's where it's most stable at. So then that's what's called the ground state. So this would be the ground state. So where the electron is in the most stable configuration, which would be the first shell in this case, since there's only 1 electron. And then let's say those 5 hydrogen atoms absorb energy of different, they absorb energy that is of different energy. So that's what the different colored arrows here are trying to represent. So that's either heat or radiation coming in, electromagnetic radiation, and they're of different wavelengths or different frequencies, or being heated to a different temperature. So, and what happens when you heat them is they start moving faster, and then if they collide with enough energy, the electron can absorb that energy and promote to a higher shell. Okay, so we have 5 hydrogens, each absorbing different energies, so the electron can be promoted to a different shell. So let's say maybe the electron moves to the second shell. Or maybe the electron moves to the third shell. So maybe it moves here to the second shell, right? Or maybe it moves to the third shell. So we'll just consider the first 6 shells just to illustrate the concept. Maybe it moves to the 4th shell. Maybe it moves to the 5th shell. Maybe it moves to the 6th shell. It could move to any shell, right? Depends on the energy that's provided to it. Okay. So what happens when the electron, so this would be what are called excited states. Right, so these electrons are more energetic now, so they're less stable. They're less stable, so that's what they're said to be in the excited state, because they're not in their ground or most stable state. So what happens when the electron is excited to a different shell? So if it's excited to the 2nd, 3rd, 4th, 5th, or 6th shell, for example, does it stay there forever? And the answer is no, it does not. Eventually and very quickly, it will move back down in shells. And so to go up in shell, it has to absorb energy. And then if it's going to move back down in shell, so once it's excited, then it could move back down. And if it moved back down in energy and goes back to any lower shell, then it has to emit energy. Okay, so if it moves back down in shell, then in doing so, it will emit the energy that it absorbed. Okay, so when moving up in shell, when moving up in shells, the electron absorbs energy. So of these shells, if we only consider the first 6 shells, so which transition will absorb energy of the longest wavelength? And if you remember from the first lecture, long wavelength means low frequency. So if it's going to absorb energy, then it's going to move up in shell. So it starts at n equals 1. Which one's it going to go to? 2, 3, 4, 5, or 6? If it's going to absorb energy of the longest wavelength, lowest energy, well, if you remember our low frequency, that means it's going to be low energy, right? So which do you think would require the least amount of energy to promote it to the second, third, fourth, fifth, or sixth shell? Well, it's going to move from the n equal 1 to the n equal 2 shell if it's low energy. And so which will absorb energy of the short wavelength? So that this means high energy. And that means high frequency, right? If it's short wavelength, it's high frequency, and that means high energy. So it would move from the n equal 1 to the n equal 6 shell if it's going to be highest energy absorption of these 6 possibilities. Okay, and then once in the excited state, which transition will emit energy of the longest wavelength? So long wavelength means low energy, right? And low frequency means low energy. So let's say it started in this, which will emit energy of the longest wavelength. So that would be starting in the 6th shell and moving all the way to the 1st shell, right? The bigger the jump, the greater the energy involved. Or once in the excited state, which transition would emit energy? So that means it's going to go down in shell, which would emit energy of the short wavelength. That means high energy. Wait a minute. Low energy would be not this. The lowest energy would be 6 to 5, right? The smallest possible jump. And which would emit energy of the shortest wavelength, so that's high energy. And high frequency means high energy. So that's going to be the biggest jump from 6 to 1. Okay, so for hydrogen, we can calculate the energy involved when an electron moves between the shells and using this equation. So E equals negative 2.179 times 10 to the minus 18, so that's what's known as Rydberg's constant, times 1 over n final squared. So n final, NF is the shell that electron ends up in. And n sub I, that's the shell the electron starts in. So let's do a calculation to illustrate this. So let's calculate the energy. So let's say it starts in the 6th shell. The electron is in the 6th shell to begin with, and let's say it moves to the 2nd shell. So it goes from 6 to 2. And then when it does that, it has to emit energy, right? It has to give off energy in the form of electromagnetic radiation. A radio wave, a microwave, a IR, visible light, UV ray, X-ray, or gamma ray. So let's calculate the energy involved using this equation. So when it moves down in energy, it could go anywhere. It could go from the 6th shell to the 2nd shell, could go to the 3rd shell, could go to the 4th shell, could go to the 5th shell. And each case it would give off energy. So let's assume it goes from the 6th to the 2nd shell, and let's calculate that energy. Okay, so 1 over n final. So the equation n final is where it ends up at. It ends up in the 2nd shell. So this will be 1 over the 2nd shell, and then square that. And then it starts in, so n sub I is where it starts at, so that's the 6th shell, so we want to square that. Okay, so 1 over 4 minus 1 over 36, and take that and multiply it by negative 2.179 times 10 to the minus 18. So this would be the energy associated with moving between the 6th and the 2nd shell. So what does it mean that the energy is negative? That means that the electron gives off energy, so energy is emitted in the process. So we can calculate the frequency of that energy using this equation, which was shown in the first lecture. So E equals h nu. Okay, so we want to solve for frequency, right? So nu is frequency. H is a constant. So just rearrange that equation. Frequency is equal to energy divided by Planck's constant. So we're going to take the energy, and we just need the magnitude of the energy. So we can drop the sign at this point because you can't have a negative frequency. So all that we need is the magnitude of the energies. So, and then we're going to divide it by Planck's constant, 6.63 times 10 to the minus 34 joules seconds. So that would be given to you. So then if you notice in the calculation, joules are going to cancel, and your units are going to be 1 over second. 1 over seconds is frequency, right? 1 over second is a hertz. So if you calculate that out, then you get the frequency, 7.3 times 10 to the 14 inverse seconds, or hertz. Okay, so now let's convert that frequency to wavelength. And so to do that, then we need this equation, which relates frequency and wavelength, right? C is the speed of light. So rearrange that to solve for wavelength. So wavelength is the speed of light divided by the frequency that you just calculated. So we plug in the speed of light, plug in the frequency that you just calculated, and you get a wavelength of 4.1 times 10 to the minus 7 meters. Okay, so let's convert that to nanometers. So if you remember, nano is 10 to the minus 9, so that means there's 1 nanometer is 10 to the minus 9 meters. So let's convert meters to nanometers. So then we need the meters on bottom, and then meters will cancel, and now we have nanometers, so that would be 410 nanometer. So when this electron moves from the 6th shell to the 2nd shell, it gives off 410 nanometer electromagnetic radiation. Where is that at? That's in the visible region of the spectrum. Right, it's violet light. So that's a number that we've seen before, the 410 nanometer. If we go back to the first lecture, the hydrogen emission spectrum. So when you heat hydrogen gas, if you remember that hydrogen in the cylinder with electrical discharge heats hydrogen to a very high temperature, and basically what that does is it promotes electrons to higher energy orbitals. Electrons from that electrical discharge, the electron moves from the n equals 1 shell to the n equals whatever shell. So if the electron happened to end up in the 6th shell and then it moved back down to the 2nd shell, then it gives off 410 nanometer light. And so where does the blue, green, and red light come from? Well, that would be the transitions from other shells. So this would be from the 5th to the 2nd shell that gives off blue light, 434 nanometer light. If it's moving from the 4th shell to the 2nd shell, then that gives off 486 nanometer light. And if the electron was in the 3rd shell and moved to the 2nd shell, then that gives off red light. Okay, so basically you see this depicted several different ways. So I've depicted it with an atom where the electron moves from the 6th shell and it ends up in the 2nd shell. So when it does that, it gives off energy. It gives off energy in the form of violet light, 410 nanometer light. Sometimes you see these diagrams on the right used to depict this. So we have basically like the rungs of a ladder. So the most stable at the bottom, n equal 1 shell. So here we have the electron starting in the 6th shell, and then it moves to the 2nd shell. And so when it does that, the electron has to give off energy. It gives off 410 nanometer light. So if you notice on these rungs of the ladder, if you notice they're not equally spaced. So this is energy on this axis. So why are they not equally spaced? Well, it's reflecting this equation, right? If NF and NI are close together, then that's going to be less energy that's given off. And furthermore, if NF was 7 and NI was 6, and you squared those and took the difference, right? That difference in energy would be a lot smaller. You can just do the math yourself. So if you plug in 7 here and 6 here, or you plug in 3 here and 2 here, well, 1 over 7 squared minus 1 over 6 squared is a lot smaller than 1 over 3 squared minus 1 over 2 squared, right? So basically, the closer a shell is to the nucleus, the more stable it is. And once the shell is so far from the nucleus, like 6th shell, 7th shell, then the energy gap between those shells is very small. But closer to the nucleus, the energy gap between the shells is much, much larger. But if the electron started in the, I guess, 1, 2, 3, 4, 5, yeah, it's in the 6th shell there. So the smallest energy emission would be going from the 6th shell to the 5th shell, right? The largest energy emission would be going from the 6th shell all the way to the 1st shell. And so what we calculated is from the 6th shell to the 2nd shell, and that's the one where it gives off 410 nanometer light. So if it started in the 5th shell instead and moved to the 2nd shell, then that's going to give off a light of longer wavelength, which is lower energy, right? So 5th to the 2nd would be lower energy. If it was in the 4th shell and moved to the 2nd shell, then that would be even a smaller energy gap. So that's longer wavelength light, that's 486 nanometers. Or if it was in 3rd shell moving to the 2nd shell, then that would be even less energy because it's a smaller jump, so that would be longer wavelength light as well. Okay, so the electrons moving from the 6th shell to the 2nd shell gives off electromagnetic radiation at the edge of the visible region. So, right, this is red, orange, yellow, blue, green, indigo, violet. So this is, remember, this is low energy because it's long wavelength to high energy because it's short wavelength. And so that's at the edge of the visible region of the spectrum. So if the transition was, instead of 6 to 1 or 7 to 2, if it was higher, say, energy, or what am I doing here? So we did 6 to 2. So what if it was 6 to 1 instead? Then that would be a bigger energy gap, right? So is that going to emit energy of higher or longer, or higher energy or lower energy? Would it be higher frequency or lower frequency? Would it be longer wavelength or lower wavelength? Well, the bigger the gap, the higher the energy, the shorter the wavelength, and the higher the frequency, right? So if the electron happened to move from the 6th shell all the way to the 1st shell instead, then that would emit light of higher energy. Do I have that? Yes. So we're here in the visible region with the 410 nanometer, right? That's violet light in the visible region. So, and that's for a 6 to 2 transition. So if you went from 6 to 1 instead, then that's going to be higher energy, which means it's going to fall somewhere to the left of the visible light. So that would, if the 6 to 1 transition happened, maybe that gives off a UV ray or an X-ray or a gamma ray, right? You would just have to calculate the energy, see what that frequency and wavelength is to know which region of the electromagnetic spectrum it falls in. But the point is, other transitions are happening too. These are just the only ones that you can see with the naked eye, because this is the region of the electromagnetic spectrum that humans can see, right? We can see from red to violet light. But transitions from 6 to 2, 5 to 2, 4 to 2, or 3 to 2, other transitions could be occurring. You just can't see them because they fall out of the visible region of the spectrum. Okay, so hopefully that made sense. So the colors that you observe in fireworks is simply due to electrons being promoted to higher energy orbitals from the heat of the explosion. And then those electrons are now in excited states, they're higher energy orbitals, and then they start falling back to lower energy orbitals. And when they do so, they give off light of different wavelengths, different frequencies, and hence different colors. Okay, lastly in this lecture we'll cover two fundamental principles from quantum theory. One is what's known as the HeisenbergUncertainty Principle. Basically what this says is that you cannot know both the position and the momentum or speed of an electron at the same time. right? If you know one, then you don't know what the other one is. If you know how faster the electron is going, you have no idea where it is. If you did the calculation, the calculation would show, well, the error in knowing where the electron is at is bigger than the size of the atom itself, right? And the other basic principle is that energy is quantized, and we've said a little bit about this. So this is where we'll end the lecture at, is just explaining what this concept means. So we gave you this context in terms of an atom. So electron can move from one shell to another shell if the light or the energy that it absorbs matches the gap in energy between those shells, right? So let's give another perspective on this to understand what energy is quantized means. So let's use a basketball analogy. So let's say you're shooting baskets at a 6-foot go and a 10-foot go. So if you give the basketball enough energy to reach this height, can you make the 6-foot go? Can you make the 10-foot go? So we'll contrast this from classical physics to quantum physics. So if you shoot the basketball to height A, no, you cannot make the basket in classical physics. So this will be like projectile motion in classical physics. And no, you cannot make it in the quantum world either. What if you shoot the basketball this high? So in classical physics terms, could you make the basket? And the answer is yes, because it would just, projectile motion, it would just maybe fall through the hoop, right? So in classical physics, yes, you can make the basket. In the quantum world, no, you cannot make the basket. If you shot the basketball this high, could you make the 6-foot go? Yes. Could you make the 10-foot, but not in the quantum world, right? Because if you made it here, then it could just go there. And if you shot it this high, could you make the 6 or the 10-foot go? Yes. You can make the, so this would be, yes, you can make the 6. Yes, you can make the 6 here. Yes, you can make the 6 or the 10-foot go. But in the quantum world, no, you can still not make a basket. So if you want to make the 6-foot go or the 10-foot go, what do you have to do? Is you have to give the basketball this much energy. So we'll call that E. If you want to make the 10-foot go, what do you have to do? You have to give the basketball this much energy. We'll call that F. Right, so if you, in the quantum world, if you want to make the basket, if you want the transition to happen, so this could be electrons moving between shells, if you want the transition to happen, you have to give it exactly the right amount of energy. So you have to give it E amount of energy to make the 6-foot go, or to make the 10-foot go, you have to give it F amount of energy, right? You have to give it exactly the right amount. So if you want to move an electron from the 2nd to the 6th shell, how much energy do you have to give it? You have to give it that much, right? We calculated this earlier, which is that frequency, which is 410 nanometer light. So if you want to move the electron from the 2nd shell to the 6th shell, you have to give it 410 nanometer light. Once it's in the 6th shell and it goes to the, if it wants to move back down to the 2nd shell, then it would have to emit 410 nanometer light. So if you gave the electron 408 or 406 nanometer light, that's shorter than 410. So is that higher or lower energy? That would be low. That would be higher energy, right? Because shorter wavelength is higher energy. So this is plenty of energy to move from the 2nd to the 6th shell, but does it happen? And the answer is no. Why not? Because it's not 410 nanometer light. If you want to do transitions in the quantum world, you have to give things, electrons, the exact amount of energy that they need. Otherwise, if you give it the wrong energy, then the energy just goes right through the atom and nothing happens, right? So that's what it means for energy to be quantized. If you want electrons to move between shells, you give it exactly the right amount of energy that it needs in order to promote to higher energy shells. Okay, hopefully that made sense. We'll stop there, and then I think we'll finish chapter 7 with the next lecture.